All right, let's get started. So this is our last class, right? So we're gonna finish talking about everything, right? So any questions in general? Okay, great. And you all got your midterm grades, right? Hopefully, yes. Okay, great. So in the last lecture, we finished talking about the spectral efficiency, right? And then we talked about the error probability, right? So the goal to talk about error probability is to figure out, so what's the trade-off between the spectral efficiency and the energy efficiency, right? So where the energy efficiency is a function, the error probability is a function of the energy efficiency, so which is the signal-to-noise ratio in our case, okay? So for the spectral efficiency, let's recall that our goal is to achieve high data rate using the bandwidth as small as possible, right? And then, yeah, we denote TS as a symbol duration and the RS as a symbol rate. And so the modulation order is denoted by this, right? So basically, the number of the signals that we're going to transmit it. Okay, and basically, this is so this is the number of bits we can transmit per symbol, right? And so we have seen this kind of thing long time ago, right? So basically, here we can see that for BPSK, M is 1 bit per symbol, and for 4PAN, and M is 2 bits per symbol. And then we can compute the bit rate, which is equal to M bit per symbol times the RS symbol per second, right? And then we have M times RS bit per symbol. Okay, so this is a bit per second, right? So this is a bit per second, and then, so if we normalize it by the bandwidth of the signal, right, or we say the bandwidth of our channel, right? So normally, yeah, we'll make our signal bandwidth at, as close as to the channel bandwidth as well, right? So basically, then we normalize it by the bandwidth. So basically, now we have a new concept called spectral efficiency, so which is measured as bits per second per hertz. Okay, and for example, for Wi-Fi, let's say Wi-Fi 304, then we have 54 megabits per second. There's no H here, right? 50 megabits per second, and then we normalize it by the bandwidth, which is 20 megahertz, and then we have 2.7 bits per second per hertz. Okay, so normally, this kind of number is the spectral efficiency, right? And we're gonna see why we have this kind of small number here very soon, right? And now the question is, how can we evaluate that in the system that we have studied, right? So which is the kind of sample-based system, right? So we have a continuous time signal, and then we sample it, and then we have a symbol rate and so on, right? So by using a Nyquist sampling rate or sampling frequency, then we can see that, okay, so the bandwidth here, the bandwidth of the channel has to be at least 1/2 times TS, because the Nyquist sampling rate, right? So the reason we have to have at least this is because if we use this as a Nyquist sampling rate, then we need the signal to be passing the system, right? And for this, basically, yeah, we have concept of pieces of information. So one piece is basically one sample, right? One sample in PAM means one symbol, right? And for the double sideband signaling, then basically, so we need to multiply 2 here, right? Because for the DSP, so the bandwidth is doubled, right? Because both sides count. Okay, and this basically means that the minimum bandwidth we need to have is 1/TS, right? So TS here, remember that's the symbol duration. It's also the sampling duration if we do the sampling, right? So very good. And then so in order to see how we compute it, so we introduce a concept called linear memoryless modulation. So one example of this is that, so linear basically means this, right? So we have something like this, so we call that linear. And memoryless basically means that, so one symbol duration, we just transmit one symbol, right? So so the waveform, all this pulse shaping, so we'll not go beyond it, beyond one symbol duration. Okay, it's called memoryless. All right, and for example, BPSK for PAM, so that we're most familiar with, they're linear and memoryless modulation, right? But for the FSK, BFSK, so it's not, right? Because it's a frequency modulation. It's not linear. Okay, in this case, in this way, so basically what we can do is that we can approximate the bandwidth by 1/TS, all right? And then using that, when we compute the spectral efficiency, so here is the bandwidth. So yeah, so here is the symbol rate, right? M times RS, RS is 1/TS, right? So TS here canceled, we have M bits per second per hertz, right? That would be our spectral efficiency, right? So which is very nice to compute, right? Very easy, just small m, right? Small m is nothing but log of the modulation order, right? If it's BPSK, then m is 2, small m is 1, then spectral efficiency would be 1, right? If it's 4 PAM, then spectral efficiency would be 2 bits per second per hertz, right? Therefore, you can think, okay, this m would be like 1, 2, 4, 8, 16, and so on, right? Would be this kind of number, okay, approximately, right? So this is the spectral efficiency. And so in practice, so what we can do is that we can use spectral efficiency to compute the bit rate, right? So actually, the bit rate is what we really care about in practice, right? Because that is the actual kind of performance we're getting via Wi-Fi or via 5G and so on, right? So if for Wi-Fi, if the bandwidth is 20 megahertz, and then we can see the bit rate would be 20 megahertz, a bit per second per hertz, a bit per second, right? If it's 4 PAM, we can get like 40 megabits per second per hertz, right? So you can see because the 4 PAM has a better spectral efficiency compared to BPSK, so that is better in that case, right? So now the question is that are we even using BPSK over 4 PAM, right? So we're actually using this kind of modulation in practice. So why we're doing that, right? The reason is that spectral efficiency is not the only metric we care about. So we care about the reliability or the energy efficiency of the system. So which can be characterized by the error probability, right? So basically it means that for 4 PAM, so it is easier to make a mistake compared to BPSK under the fair comparison, okay? So then we introduce the way to compute the error probability, right? So basically the error probability is defined as the probability that a symbol is in error, right? For example, if we send a 1, then we think it's a 0, then means that we're making a mistake, right? So basically, our goal is to compute the PS, right? So in order to compute that, so we basically break it into 2 cases for the into like different cases, right? So for example, consider when SI is sent, then we consider symbol rate of that, right? Then in order to compute it, we just need to multiply the probability of SI sent, and then we sum over all the possible i's, right? And you can think that so the probability of SI is sent is equal, right? So basically, we just need to average of all of them over I, and then you're gonna get the PS, right? That's basically the idea. And in order to compute it, so we can write it out, it's equal to this, right? So basically, given SI sent, and then what's the probability that we're making a decision of Sj where J is not I, right? That means a mistake, right? So this is the probability that we really want to compute, right? Computing that is not that easy, not trivial, okay? So then we start from the binary case, right? Binary case is when we can characterize it exactly. Okay, so basically in that case, in this case, we have 2 cases to consider. One is when S0 is sent, then we think that is S1, or when SI is sent, we think that is S0, right? So we have 2 cases, and you can think, the system is pretty symmetric, then basically probably they're the same, right? And then we just focus on one of them, right? So now we only talk about one rule for decision, so which is ML rule, right, or map, right? But under this case, given S0 and S1 will be sent with equal probability, so we have a maximum likelihood rule. So in order to make a mistake, so basically what we need to do is to see, so when the distance of the received signal and S1 will be less than the distance between the received signal and S0, right? Given S0 is sent, right? So this is the condition of the mistake, right? It's the distance, Euclidean distance rule, right? And then, so basically, if we draw the signal constellation, so it will look like this, right? So we have, so this will be S0, and this will be S1, right? And the magnitude of that is square root of E here, and distance of that is 2 times square root of E, right? And given this, so we can see that, so those would be, so the area here is a probability that we're making a mistake, right? Because we're setting S0, so this would be the PDF of FR given S0, right? And now, so basically, this region is where we are going to decide S0, and this region is when we decide S1, right? So then we need to look at this region. But the probability that we're sending S0, but R is in this region will basically be the area here, okay? And then, so then we can use the integral to compute that, and then we can see that as we can represent this as Q function. Okay, remember the definition of Q function is then we consider, okay, when, if this is in the middle, right, and then, so this area would be just a Q function of this value here, right? But this value is the distance between this and that, right? So then this is what we're writing here. So distance from the threshold to the mean, right? So this is the mean, this is threshold. So this distance would be what we're going to put into the Q value, right? But because for the Q value, we consider a standard normal distribution, then we need to normalize it by standard deviation of noise, right? Okay, great. And then in this case, so we can see, okay, so this is nothing but, so this distance is the whole distance divided by 2, right? So distance divided by 2 and divided by standard deviation of the noise, which is this, right? And plug this in, so this is what we get, right? 2e divided by n0 and square root of it, so that will be what we get for the error probability of b plus k, right? And remember that, so as 1 is n will be the same, equal to that, right? Then basically this would be the total error probability in the end, right? Okay, yeah. And then we need to talk a little bit on this, right? So we can see, so this term E over N naught, so this term is very important. So for any constellation, we're going to see this term somewhere, right? The difference is that we're going to have different coefficients in front of it, right? So in this case, so we're going to, yeah, so this is what the bullet one. So basically, we give an example in class, right? Let's say if the probability of error is 10 to the power minus 5, and then from here, this basically means that this equals 10 to the power of minus 5, right? And then, so we can see this value inside of the Q would be given by the inverse function of Q, right? In this case, would be 4.26, right? How to get it? You can use Python, or you can use just Q table to do that. Right, normally, for an in-person exam, so you're going to use the Q table. But if you take home, then whatever, yeah, you can use anything. But normally, we studied that, so we just use Q table to compute that. And hence, so basically, we can compute the signal-to-noise ratio basically as this number, right? So now let's take a look at the Q table. So let's see how we can do that. So basically now we know this probability is 10 to the power minus 5, right? Remember that. And now we're using a table to figure out what should be the value of this guy, right? So what is the inside value to make the Q function equal to this, right? So normally this is what Q table look like, right? So hopefully you can see that. So basically, those values are probabilities, right? And those values are x, okay? And the value on the top basically means that, so this value and plus whatever there, right? For example, if for this value would be 1.1 and another one, so 1.11, right? And for this value would be 1.1, this 0.02 would be 1.12, right? So for our case, so what we're looking for is 10 to the power minus 5, or 1 times 10 to the power minus 5, which is not here yet, right? Here only up to 10 to the power minus 2, right? So we need to continue looking at this. So there's one more page, and this is and this is where we want to find, right? So yeah, roughly speaking, so this would be 10 to the power minus 5, right? You can now find the exact value here, right? 1.0221, I think that's close enough, right? And now we need to figure out what is the x to achieve it, right? Then we can find this 4.20 here, right? And on this this direction is 0.06, and then we'll add those two together would be 4.26. Okay, so this is how we use the Q table. That clear? Yeah, probably nobody is using this in this way now, but that's yeah, that is usually how we do that. Okay, so we get this 4.26 in this case. Right? That clear? Okay, any questions? All right, so then I think we're gonna keep talking about that. Yeah, hopefully this will not be dead. Okay, great. So in this class, we're going to finish talking about the error probability. Okay, so let's see one more example for the binary case. Okay, so for the binary case, we see a BPSK or the antipodal case, right? So now let's see another common example, so which is BFSK. Okay, BFSK basically means that the binary frequency shift keying, right? It's a frequency shift. Basically, it's a frequency modulation. So basically, it's very similar to the BPSK case, but the difference here is, so BPSK, we can think that as a phase shift, right? So one is 0, the other is with a phase of pi, right? But we can take the pi out to make it a minus, right? So, but here is it's a frequency shift keying. So basically, what we're doing here is that we can use kind of orthogonal frequency to represent each of them, right? So basically, this is S0 and S1 would have the same. Yeah. Right, you can see that, so this will be S0, this will be S1. The difference here is that we have F0 here and we have F1 here, right? So I have different frequencies. And by picking the right frequency, so we can make sure that these two are exactly orthogonal to each other, right? So yeah, we just want to, so we don't show how to do that, but it's not that very hard, right? Just compute the inner product between these two guys and figure out what is the difference between them to make them orthogonal to each other, right? And so basically, in this case, we can draw the constellation, right? So this direction would be F0 t, this would be F1 of t. So our goal is to make them orthogonal, right? So basically, we can think FSK is an orthogonal modulation instead of antipodal modulation, right? So in this case, so we can see, so this is S1, and this would be S0 square root of E, right? We kind of have seen one example like this before, but it's not exactly like the BFSK, right? Which is another waveform here, right? Oh, by the way, this PT is just a normal PT that we're considering. It's given by this 10 t, right? So this is a normal PT that we're considering, right? So this is the signal constellation. So after doing the receiving, the receive processing, right? By multiplying the base function and then do the integral, right? And from here, so basically you can see that, yeah, this would be our signal, and this would be the distance, right? So which is square root of 2e, right? So that would be the distance, okay? And in this case, obviously, so the decision rule in this case, the ML decision rule in this case will be the same as before. So basically what we're going to do is we're going to draw a line here, right? If the receive signal is here, then we're going to say we receive S1. And if the receive signal is here, then we're going to decide the receive signal is S0, right? Distance-based rule, right? Same. Okay, so given that, so we can write the error probability, right? Using the same formula as before, the error probability in this case is nothing but Q d over 2 divided by naught over 2, right? So we can, yeah, if you don't think it's true, then just compute it. So you're gonna see, so it will be still like that, okay? So this will be the error probability, so which is the same formula that we were using before. So then, so the difference here is basically this guy, right? Here is d over 2, right? The distance here now is square root of 2e. Then we're gonna compute it as square root of 2e divided by 2 divided by the naught over 2, right? So in this case, so we're gonna see, so this would be, so this 2 will be go up and this 2 will be go down. 2 will be canceled, right? So this will be nothing but q square root of E over n naught, right? So this will be error probability for the orthogonal, binary orthogonal modulation. Right, does that make sense? Any question here? Right, you can think, it's the same as the binary, but just rotate it a little bit, and then everything else will stay the same. Okay, so So now let's summarize a little bit. So basically, for BPSK, or that is the antipodal case, and then we consider BFSK, so which is the orthogonal case, right? So in these two cases, for BPSK, the error probability is given by this, right? And for this case, the error probability is given by this, right? So you can see the difference here is what? It's basically here, right? So those are the difference. So which, we kind of said that before, right? For the antipodal, so the distance between these two signals would be larger than that of the antipodal case, right? So in this case, okay, so which one is better? Or which one is smaller in terms of error probability? Given the same E, of course. BPSK, right? Because this guy is larger, right? So remember, for the Q function, so basically what we're going to characterize is basically this area, or the other one, right? So if the inside is larger, basically it means this will move to the left, right? Then the error becomes smaller, right? Just remember, for Q function, if this is larger, then the value will be smaller. So we have a larger value here, so this guy will be better than this guy, right? So now let's figure out. So let's see how much better for this guy, right, compared to the other one, right? So basically, let's say if we denote EA as the energy for this one, for antipodal, and denote E orthogonal as the energy for orthogonal. Okay, so in this case, so in order to get the same error probability, right, we need to make sure this and that will be the same, right? I say to get the same error probability, then what we need is 2 times EA divided by N naught should be equal to this, right? E over E orthogonal over N naught, right? So we ignore the square root, right? So this has to be equal to that. So then what does that mean, right? In order to make those two are equal, so basically we need to increase, right? So this energy by a factor of 2, right? So basically it means that ER has equal to 2 times EA. Then we can make these two equal, right? In other words, in dB, so this basically means that E orthogonal dB will equals to EA dB plus 3 dB, right? So a factor of 2 is the 3 dB, right? So basically we need 3 more dB to achieve the same performance if we use orthogonal modulation, okay? Or the BFSK is 3 dB worse compared to BPSK. So in terms of the energy efficiency. Okay? Is that clear? Okay, great. All right, so yeah, this is what we do for the binary case. Okay, so now let's see what should they do for the general case. Okay, so let's see the error probability for MRE modulation. Okay, so let's see how we can do that. So first, we're gonna recall the general formula, right? Because now we're considering the general case, right? So the general formula for the error probability is as follows. So we consider PSI, right? The meaning of it is basically when SI is sent, then what is the error probability, right? So this equals to the probability that we're going to decide that SSJ, and so J cannot be I because we're making a mistake, right? Then given SI sent. Right, so this is the general probability, right? So evaluating that is generally hard, right? For example, normally the constellation, can be, arbitrary, right? Or, it's not that simple. So evaluating that can be hard. So what we're basically doing here is as follows. So what we do is that we use a union bound for the probability. So to break it, right, to move it out as a summation, right, sum over all the I not equal to J, and we have this. Right, does that make sense? Okay, this is just union bound, right? So union means or, right? So if we make that a summation, then that will give you upper bound, right? It's just a union bound. But in addition to that, so we assume this guy have a very special meaning here, right? So we consider that as a pairwise error probability. So what does that mean? So basically, it means that we're just deciding between these two, right? We're just deciding whether, it's either SI or SJ. That's it. Okay, it's a pairwise. So that's a BPSK. That makes sense. Okay, you may think it's not optimal. Yeah, that's right. The reason we can somehow do this is that, so for the, I didn't draw it. For the Gaussian distribution, like that. Okay, it's a very special kind of distribution. It concentrates pretty well in the middle. So everything here would be extremely small. Okay, so if we're thinking, something further apart, it may not matter anymore. If we still add some of those, it doesn't matter too much, right? Although it matters, right? So, but this is strict upper bound, right? It's not approximation, it's the upper bound, okay? So this is basically the idea, like pairwise probability, okay? And now the problem solved, right? So this is how we compute it, right? That easy. And we denote that as Pij. Yeah, Pij. So this is a pairwise probability. And then, so now we can write down what's the value of it, right? Given that's a pairwise probability, right? Because, so pairwise, again, so basically means that we consider this as a BPSK, right? So the probability of each term would be what? I mean, maybe I'll use another color here to make it more explicit. So basically, this guy will just equals to what? Q d over 2 square root of n naught over 2. But this d is dij, right? The distance between I and j, right? So each of this would be like this, right? And here, so the dij is nothing but the distance between the signal Si and the Sj, right? So each of them is that. So yeah, given that, we can write down the PSI. Right, so now PSI would be equal to summation of j not equals to I, and then Q dij over 2 divided by square root of n naught, right? So again, so this upper bound is usually called the union bound upper bound, right? So this is union bound upper bound. Okay, which is not accurate, but it's a strict upper bound. Right, let's see an example. Okay, so we're going to see the example that we have seen many times. So that's 4-pen, right? For 4-pen, so our signal constellation looks like this, right? So basically, we have 4 points. So here is S0, S1, S3, and S2. Okay, and the value here. So we computed before. So if you don't recall, then just check our lecture notes before. So this is ES over 5, and this is ES over 5 times 3, and this is minus ES over 5, and this is minus 3 times ES over 5. Right here, clearly the distance is what? Distance is, this minus that is 2e square root of ES over 5, right? And so now let's consider S0 is sent, for example, then the distance is D01. D01 equals to that. Okay, and how about this? So this is D03, right? So that equals to 4 square root of ES over 5, right? Okay, so so now given this, so we can think. So let's say S0 is sent. So basically, PS0 equals to what, right? So now we're going to use this formula, right? So basically, we're going to add 0, 1, 0, 2, and 0, 3, right? So basically, what we get is that we know, yeah, this is an upper bound. So we have Q D01 over 2 divided by N naught over 2, right? And then we have 0, 2, right? And then we have D03, right? We have 3 terms here, right? Okay, and then let's plug that in to see. Yeah, I'll probably write here. So that is too low. So this equals to, yeah, we can see D01 equals to this, right? And 02 is this distance, will be the same as that, right? And 03 is something bigger, right? So basically, we can combine these two together. So that'll be 2Q, and we plug that in. So D0 is this one, right? It's 2 square root of ES over 5 divided by, and then we need to divide it by 2 here, right? So then we don't have this 2 here. Okay, and then add this one, right? This one divided by 2 is 2 times square root of ES over 5. Okay. Yeah, so this is basically what we got. And we can simplify this a little bit. Right, so this is square root of 2ES over 5 over 5 and naught. And this guy is 228 ES over 5 and naught. Right, and then this will be upper bound for the error probability. Right, by symmetry, so we know, so this guy will equals to P as 1 as well. Right, because S1 is totally symmetric. Okay, yeah, for the other two, it'll probably be different, but we can use a similar idea to compute it. Okay, so any questions so far? Is that clear? Okay, great. And yeah, let's see. Yeah, as we said before, so this pairwise thing is upper bound, right? So yeah, let's take a look at detail on why it's upper bound. So basically, yeah, let's draw the PDF here. Right, let's again assume S0 is sent. So this is the PDF of when S0 is sent, right? So when S0 is sent, so basically here is the square root of ES over 5. Right? This is PDF of R given S0 is sent, right? So here we have S1. And let's do this again. And here is S2, and no, here that's S3, S3. And here is S2, right? So this is basically what we do. Okay. All right, nice. So basically, so now let's see. So yeah, when we decide, yeah, so basically what we do here is like this, right? We consider a pairwise probability, okay? So when we consider the pair between S0 and S1, so this would be the probability that we're going to determine there's an error, right? And then, so when we consider the pair between S0 and S3, right? And then, so basically, we're going to decide this would be our error. Okay, correspondingly, so that will be, so this will be between 0 and 1. This will be between 0 and 3, right? Then we're going to add these two probabilities together. Okay, so basically here we're going to add the green one and the red one together, right? And here the problem is what is this, right? So we added twice. Okay, so that's not good. Okay. So although it's upper bound, right, it's approximation, but how, I mean, there's some obvious problem here, right? So how can we solve this problem? It's pretty obvious, right? So how? Yeah, because when we consider this pair, so the green would be our probability, and when we consider between S0 and S3, the red would be our probability. We add them together, right? And all the red part is redundant. Right? How to solve the problem? Yeah, just ignore the red, right? See, so what does that mean here? So basically, it means that we only need to consider the error probability, the pairwise error probability between this and the nearest neighbor. And for the farther neighbor, we just ignore that, right? That makes sense? So basically, that's our solution, right? So in practice, so what we're going to do is that we're going to only consider the pairwise error probability of our neighbors and ignore everything outside, right? By neighbors means the closest neighbor, okay? So basically what we do is we're going to do a nearest neighbor approximation. So now it's approximation. It's not necessarily as upper bound. Nearest neighbor approximation. Okay, so in this case, let's denote nearest neighbor, NI, so that as the nearest neighbors of SI. So it's a set of the nearest neighbor of SI, right? So basically, the error probability SI will be given by all the J or Sj inside this set, and then we sum over it, sum over the Pij. Okay, so basically that equals to Sj in Ni, and then this is Q Dij over 2 divided by this, right? So basically, this formula is what we use to approximate the error probability in practice. Okay? Only consider nearest neighbors. That makes sense? Okay, so this is the formula that we're using. So by using this, and for that example, so we can see that for P S0, right? And now for S0, we only consider the distance, the error probability between S0 and S1 and S0 and S2, right? And in that case, they're the same. So that's 2Q square root of what? 2ES over 5 and naught, right? So this is a probability that we're in error when S0 is sent. Okay, and in that case, so we can easily compute P2 and the PS. So yeah, of course, this is equal to PS1, right? But when for PS2 and S3, so it will be slightly different, right? So when we consider S2, right, then we can see on the other side there's nothing. On this side, it only has one nearest neighbor, right? So in this case, so PS2, and it will be equal to PS3 as well. You can see they're symmetric. PS3, then that'll be equal to just one term here, right? So which is the Q inside distance is between these two guys. So that'll be the same as this, right? It's 2ES over 5 and naught, right? But different here is that we only have one. There's nothing here, but we have a 2 here, right? So we have a 2 here, but here there's just 1, right? Okay, here. So given this, so now we're ready to compute the error, the general error probability, right? PS. So that'll be the average of all the probability. Average of here should be P01 plus, PS0 plus PS1 plus PS2 plus PS3, right? And for PS0 and PS1, so that equals to this, right? So I have 2 times 2Q square root of 2ES over 5. And then we have 2 times this guy, right? Q 2ES over 5 and naught. Right? So now we have this 2 times 2 is 4, 4 plus 2, 6, 6. We have 3 over 2 Q square root of 2 ES over 5 and naught. Okay, so that is the total error probability for 4-pan. Okay? Does that make sense? Right? Okay, great. So now the final step is that, okay, so now we want to make some comparison between this and BPSK. How can I do that? Right, so now we need to have some, we need to distinguish a little bit, right? So here is ES, right? For BPSK, so what we got is, for BPSK, the error probability is Q square root of 2E over N naught, where this is also ES, right? But if we just compare the value of this and that for a given ES, would that be a fair comparison? Not really, right? Because now we're considered 4-pan, right? This is a 4-pan. So the spectral efficiency in this case is 2, right? For BPSK, the spectral efficiency here is 1. So we're sending less for a given time and a given frequency. For BPSK, we're sending more here, right? But if we just compare the error probability directly given a fixed symbol energy, so it's not fair. What makes it fair is to consider the bit energy, right? So basically what we consider here is that I want to make the comparison fair. So we define the bit energy as this. So the symbol energy equals to m times EB. So this is the bit energy. Okay, of course, this m is a log 2 of capital M, right? So it means per bit over, so it means joule per bit, right? So before it means joules per symbol, okay? It means joule per bit. In that case, so we can see in this case, so we're assigning 2-bit now. So this will equals to 3 over 2 Q square root of 4 EB over N naught, right? Because ES over 2 dB, right? ES equals 2 EB, right? But in this case, so this ES equals to 1 EB, so then we can do that, right? So basically in this case, so now this guy is fixed. Yeah, if we fix this guy, and then we can compare the error probability in a fair way, right? Consider same energy per bit, and then what's the error probability between these two guys, right? Yeah, does that make sense? Okay, so I have one more example. So to see, to compare the performance here, and clearly, so still for this guy, so it's in terms of error probability, so this does not perform as well as the BPSK. Okay, but I have some analysis here in my notes. You can take a look offline. Okay, so basically, I want to show you something else. Yeah, in the final 3 minutes. Yeah, maybe I want to emphasize one more thing here, right? So this one is common, right? Yeah, F means a 5 here. There should be another 5. Yeah, so what matters is basically this guy. Okay, so basically, we just need to see the value here and also the value here, right? So this is what makes it very different. Okay, in terms of the energy efficiency, we just compare that inside. Okay, so let's see. Yeah, just want to show you this. Yeah, the reason I want to show you this is because, so this is basically what we are using today, right? It's very important, and we have seen that before, the quadrature amplitude modulation, or QAM, right? So yeah, when we talk about analog communication, we very briefly went over that. I think you have some labs on that, right? So basically, this is one of the most important modulation technique for our digital communication, right? So the modulation form is given by this, right? The ES is just a symbol energy, right? But here you can see we have AIK and AQK, and I means in phase and Q means quadrature, right? And the value of A and Q are basically like 1 minus 1, 1 minus 1, right? So this is a modulation structure, right? So this is identical as what we have seen before, right? The only difference here is that before, so this A and this AIC and AIS here, or AIK and AQK, so they're like analog signal, but now those are the digital signal, right? We need to modulate that using some pulse shaping function and then do this modulation, right? Which is identical as what we have seen before. So for this kind of modulation, and you can see that, so the cosine and sine, they're not exactly orthogonal to each other, but when omega c is much bigger than 1 over t, they are approximately orthogonal, right? That's a key property here, right? So in this case, we can define our basis function as the same manner, as before, right? So we just use one of the signal, normalize it by its norm square, the square root of the norm, and with just a norm, and then for the other one as well, right? F0 and Ft, they are orthogonal. Okay, and then we can write down F0 and F1, and then, we can write down the signal space representation, right, by do the inner product between F0, F1 with our received signal, right, or with S, right? So basically, and those are the coordinates, right, on the signal space, right? And if we write it down, if we draw that, it will be like this. So this is the direction of F0, this is the direction of F1, right? So basically, the black point here are our 4 points, right? So now, so it's not like one-dimensional, it's two-dimensional, right? But now the location is like this, right? And so what makes it interesting is that, so you can think this as a case of like 2 BPSK, right? It's like 1 BPSK on this direction and another BPSK on the other direction. It's kind of like a product design, okay? So yeah, that works here, not all the time, but it works here. So in this case, we can characterize the distance between all the points here, right? For example, distance between 0 and 1 is basically this, right? And in this case, let's see, so for the ML decision region, so we can see, so if it's here, so we're going to decide it's at 0. If it's here for the yellow stuff, it will be S1. If it's the purple region, then it's S3. Otherwise, it's S4, S2, right? So basically, this would be our decision region in this case, okay? And in order to characterize the error probability, we're going to use the nearest neighbor rule. Yeah, I missed. It should be S0 equals to PS equal to PS comma 0, right? So I missed a 0 there. So and then so in this case, so you can see it's a very symmetric modulation, right? So basically, when we consider the error probability that S0 is sent, we just need to consider the nearest neighbor, so which is S2 and S1, right? We ignore that, right, because it's further, right? So and then, so we can get this formula, right? Just the D01 and have D02, right? By adding them together, because the D01 and D02 are the same, we're adding them together, and we get that, right? And then after some manipulation, so this is what we get. Yeah, there's anything wrong? Yeah, probably there's no this 2, right? There's the, oh, no, there's a, yeah, what's going on? Why? Oh, wait. Oh yeah, that's right, right? So these 2 will go up and these 2 will go down and they will be canceled, right? So this is what this is right. So this is what we get. And then in terms of the energy, the bit energy, so it will be this one, right? But if you're, so this is basically what we got for the quant. Okay, and if we think, so remember, so this is what? This is the probability that we're making a mistake for each symbol, right? Now the probability that we're making a mistake for each bit, right? So roughly speaking, if we consider the bit case, right, let's assume that, okay, so if we have an equal probability to make an error for each bit, if we make an error probability for each symbol, then we divide by 2, we got this, right? And this will be the same for BPSK, right? Basically means for quant, right? So roughly speaking, we can achieve the same error probability per bit, but we achieve like our energy efficiency is got doubled, right? We transmit 2 bits per sec, 2 bits per symbol instead of 1, right? Okay, yeah, I think that is all I want to cover for today. And oh wait, no, yeah, just one final word. Yeah, I need to wait a little bit. Okay, so basically, let's see for the schedule. Yeah, so basically, the final exam will cover everything after lecture 24, right, which is sampling. Okay, and the form will be exactly the same as our midterm, right? And the date will be April 30th, 9 a.m. And then, so it will be due on Friday, probably. That's May 2nd, I guess. So 9 a.m. Okay, yeah, and of course, yeah, this time the grading will be very fast, right? Not like a midterm, yeah. Okay, great. So hopefully you enjoy this semester, and hopefully to see you somewhere else. Yeah, thank you.